There are few substances in the world as ordinary as salt. It sits quietly on dining tables, dissolves into oceans, preserves food, and disappears without drama into boiling water. We sprinkle it without thinking. We spill it without concern. We walk on it during winter when roads are iced over. But what if we stopped seeing salt as a seasoning, and started treating it like metal? What if we heated it, melted it, and poured it into molds the way blacksmiths pour iron or aluminum? What would really happen if we tried casting salt like metal? To understand this, we first need to understand what salt actually is. Common table salt is sodium chloride, NaCl, a compound formed when the highly reactive metal sodium bonds with the poisonous green gas chlorine. Together, they form a stable ionic crystal lattice. This lattice is incredibly strong at room temperature, which is why salt forms hard, sharp-edged crystals instead of soft powder. Every grain of salt you see is part of a rigid cubic structure, locked together by electrostatic forces between positively charged sodium ions and negatively charged chloride ions. But here's the part most people don't realize: salt can melt. And not at low temperatures. Not even at temperatures you'd encounter in most kitchens. Sodium chloride melts at about 801 degrees Celsius, 1474 degrees Fahrenheit. That's hotter than most household ovens can ever reach. It's hotter than molten aluminum. It's dangerously hot, and if you want to cast salt like metal, that's the temperature you must reach. Imagine a furnace roaring to life. A crucible placed inside. Instead of iron scrap or aluminum ingots, you pour in coarse white salt. At first, nothing dramatic happens. The salt sits there, unchanged. As temperature climbs, it remains solid long after aluminum would have liquefied. But then, somewhere beyond 800 degrees Celsius, something remarkable occurs: the rigid white crystals collapse. The structure breaks down, the grains fuse, and suddenly, salt becomes a clear, almost glass-like liquid. Molten salt does not glow bright orange like molten iron. It doesn't flow like shiny silver metal. Instead, it looks translucent, faintly shimmering, and almost deceptively calm. But don't be fooled. At this temperature, it is intensely energetic. The ionic bonds that held it in rigid form have loosened just enough for ions to move freely. In fact, molten salt becomes electrically conductive. This property is so significant that molten sodium chloride is used in industrial electrolysis to extract pure sodium metal and chlorine gas. Now picture pouring that molten salt into a mold, perhaps shaped like a sword, a coin, or a simple bar. As it flows, it behaves differently from metal. Molten metals are cohesive. They cling to themselves because of metallic bonding. Molten salt, on the other hand, is ionic. Its behavior is governed by charged particles interacting in a liquid state. It flows smoothly but with a unique surface tension profile, not quite like water, not quite like metal. And then comes the cooling. As molten salt cools below 801 degrees Celsius, it begins to solidify. But it doesn't shrink and solidify the same way metals do. Metals often form grains, tiny crystals that grow and interlock. Salt, however, reforms its cubic crystal lattice in a more uniform, brittle fashion. It doesn't become tough, it becomes fragile. A cast bar of solid salt would look impressive at first glance, but one sharp impact, and it could shatter. This brittleness is one of the biggest differences between casting salt and casting metal. Metals owe their strength to metallic bonding, where electrons move freely in a sea around positive ions. This allows metals to bend without breaking. Salt doesn't have that flexibility. If you shift one layer of ions in solid sodium chloride, positive ions line up against positive ions, negative against negative. The repulsion is immediate, and the crystal cleaves. That's why salt breaks along clean planes. But there's another problem. Salt is hygroscopic to some extent. It interacts with moisture. A cast salt object exposed to humid air would slowly degrade. It might absorb water from the atmosphere. Its surface would dull, edges would soften. Over time, it would literally begin dissolving into the air around it. So casting salt like metal is possible, but is it practical? In most cases, no. The high melting point demands extreme heat. The final product is brittle and moisture sensitive. And unlike metal, salt offers no ductility, no resilience, no ability to be hammered or forged afterward. Yet the story doesn't end there. Because molten salt isn't just a curiosity, it's an industrial powerhouse. In advanced nuclear reactor designs, molten salt is used as both fuel carrier and coolant. In concentrated solar power plants, molten salt stores enormous amounts of thermal energy. Facilities like the Crescent Dunes Solar Energy Project have used molten salt to store heat collected during the day and release it at night to generate electricity. The same material that seasons your food can store gigawatts of thermal energy. The reason molten salt is so useful is its thermal stability. Unlike water, it doesn't boil at 100 degrees Celsius. Unlike oil, it doesn't degrade quickly at high temperatures. It can remain stable at several hundred degrees Celsius, making it ideal for heat transfer systems. But imagine pushing the experiment further. What if instead of pure sodium chloride, we used different salts, like potassium nitrate or mixtures known as eutectic salts? These combinations melt at lower temperatures. Some melt around 220 degrees Celsius. That's hot, but manageable with industrial equipment. Suddenly, casting salt-like materials becomes far more feasible. If you poured such molten salts into molds and allowed them to cool in controlled conditions, you might produce smooth, glassy structures. They would still be brittle, but they could be shaped with surprising precision. Transparent salt sculptures, intricate crystalline forms, objects that sparkle like ice but hold form at room temperature, until humidity claims them. And that is where science meets art. In controlled environments, artists and scientists alike have experimented with salt crystallization to grow massive cubic forms. While not cast in the traditional metallic sense, these structures demonstrate how salt can form stunning geometric solids. Unlike metal casting, however, the beauty of salt lies in its fragility. It is not meant to endure. It is meant to exist temporarily. Now imagine dropping a cast salt sword into water. It wouldn't rust. It wouldn't sink as a heavy metal blade might. It would begin dissolving instantly. Edges would blur. Details would fade. Within minutes to hours, depending on size, it would vanish completely, returning to invisible ions in solution. Metal casting creates permanence. Salt casting creates impermanence. And that contrast is powerful. So what truly happens when you cast salt like metal? Physically, it melts at extreme temperatures, flows as an ionic liquid, solidifies into a brittle crystalline mass, and remains vulnerable to impact and moisture. Chemically, nothing changes, it remains sodium chloride. Structurally, it transitions between rigid lattice and mobile ionic liquid and back again. But philosophically, it transforms our perception. We take salt for granted. We see it as soft, granular, mundane. Yet under the right conditions, it behaves like molten rock. Like lava, like industrial material capable of storing the energy of the sun. In part 1, we melted salt and poured it like metal. We watched it transform from a harmless white crystal into a transparent, searing liquid at 801 degrees Celsius. We cast it, we cooled it, we shattered it, but now we move beyond the spectacle and into the deeper question. What is molten salt really doing at the atomic level, and how far can we push this experiment? When sodium chloride is solid, every sodium ion is locked into position next to chloride ions in a repeating cubic lattice. This structure is incredibly ordered. Every positive ion is surrounded by negative ions, and vice versa. The forces holding them together are electrostatic attractions, powerful, directional, and rigid. But when you heat salt past its melting point, that lattice collapses. Not chemically. The ions remain Na and Cl, but structurally. The rigid arrangement dissolves into a fluid network where ions move freely past one another. This is not like molten metal. In molten metals, atoms share electrons in a sea of delocalized charge. That's why metals conduct electricity even when solid. Their electrons are mobile. Salt, however, cannot conduct electricity when solid because its ions are fixed in place. But once molten, those charged particles are free to move, and that movement carries electric current. This is why molten sodium chloride is used in industrial electrolysis. At facilities based on the Downs process, molten salt is split into pure sodium metal and chlorine gas. The moment electricity passes through the liquid, sodium ions migrate toward the cathode and gain electrons. Chloride ions move to the anode and release electrons, forming chlorine gas. So imagine this. You cast a bar of salt. Then you melt it again and run electricity through it. You are no longer dealing with salt. You are separating it into one of the most reactive metals on Earth, sodium, and one of the most toxic gases, chlorine. Sodium bursts into flame on contact with water. Chlorine gas was used as a chemical weapon in World War I. The harmless seasoning on your table becomes, under the right conditions, an industrially volatile material. But let's return to casting. What if we tried to alloy salt like metal? Metals form alloys because their atoms can mix within a shared metallic bonding structure. Iron can combine with carbon. Copper can combine with tin. Their atomic structures allow substitution and interstitial mixing. Salt doesn't behave that way. However, something fascinating happens when you mix different salts together. Instead of forming traditional alloys, they form eutectic mixtures, combinations that melt at lower temperatures than either component alone. For example, mixtures of sodium nitrate and potassium nitrate melt at dramatically reduced temperatures compared to pure sodium chloride. These mixtures are widely used in solar thermal plants because they remain liquid at manageable industrial temperatures while storing enormous amounts of heat energy. In fact, molten salt energy storage is a key component in concentrated solar power systems. Projects like the Ivanpah Solar Power Facility and other thermal solar plants rely on similar principles, capturing sunlight, converting it to heat, storing that heat in molten salt, and using it to generate electricity long after sunset. So what if you cast not pure salt, but a eutectic molten salt mixture? Now the melting temperature drops. The energy required drops. The fluidity changes. The cooling behavior becomes more complex. Instead of reforming a simple cubic sodium chloride lattice, the mixture may solidify into interwoven crystalline phases. The final object could have different fracture patterns, different translucency, even different thermal properties. But would it still be brittle? Yes. Because ionic solids, no matter their composition, share one fatal flaw for structural use. When layers shift under stress, like charges align, and repulsion splits the structure. There is no electron seat to cushion deformation. No plasticity. No forgiveness. Now imagine casting a salt blade and testing it against steel. The steel bends slightly under impact, distributing force along its metallic bonds. The salt blade experiences internal ionic misalignment, and cracks propagate instantly. It wouldn't dent. It would shatter explosively. However, here's where things become interesting. What if the casting happened in a vacuum? In normal atmospheric conditions, molten salt is exposed to oxygen and trace moisture. But under vacuum conditions, several variables change. Cooling becomes more controlled. Oxidation reactions are minimized. Surface impurities are reduced. The resulting salt structure could form with fewer defects, potentially increasing clarity and structural uniformity. You might produce an almost glass-like transparent crystal block. But even perfection doesn't eliminate brittleness. Now let's push the experiment further. What if instead of cooling it slowly, we quench molten salt rapidly? Rapid cooling in metals can create amorphous structures, metallic glass, where atoms freeze before forming crystals. Could salt form something similar? The answer is complicated. Ionic compounds strongly prefer crystalline arrangement. Their charged nature drives them toward order. But under extreme cooling conditions, partial disorder might occur. The structure could trap internal stresses. The result, even more fragile than before. Now imagine scaling up. Instead of a sword, cast a solid salt shield weighing 20 kilograms. You would need a furnace exceeding 800 degrees Celsius. Industrial-grade crucibles resistant to corrosion. Protective equipment to withstand radiant heat. When poured, molten salt would not sparkle like molten steel. It would look eerily calm. Almost like water. But drop a single droplet on unprotected skin and the result would be catastrophic burns. As it cools, the surface would solidify first, forming a crust. Internal heat would remain trapped temporarily. Thermal gradients would develop. If cooling happens unevenly, internal stresses could fracture the object before it even leaves the mold. Metal casters carefully manage cooling rates to prevent cracks. Salt would demand even greater precision. And then comes the environmental factor. Humidity. Salt's relationship with water is relentless. Even if your cast salt object survives the casting process perfectly, the real world begins attacking it immediately. Water molecules in the air collide with its surface. Slowly, Invisibly, dissolution begins. Edges lose sharpness. Surfaces become tacky. Eventually, structural integrity weakens. This is why salt sculptures, even massive ones carved from halite blocks, must be preserved in controlled dry environments. But there is another dimension to molten salt that changes everything: temperature endurance. While salt objects are weak structurally, molten salt as a liquid can survive temperatures that destroy water and degrade oil. That makes it ideal for nuclear reactor cooling systems, particularly in experimental molten salt reactors. These reactors use molten salt not just as coolant but as fuel carrier. The salt itself contains dissolved fissile material. If temperature rises too high, the system can drain the molten salt into passively cooled tanks, preventing meltdown scenarios. It's one of the most promising designs for future clean nuclear energy. And suddenly, our experiment shifts from curiosity to cutting-edge technology. The same material you tried casting into a sword could power cities. So what happens when you cast salt like metal? You unlock a paradox. As a solid object, salt is weak, brittle, temporary. As a molten liquid, it is powerful, conductive, energy-dense, and industrially transformative. Metal gains strength when solid. Salt gains potential when molten. And that contrast is the heart of this experiment. But we're not done yet. We melted salt. We poured it. We shattered it. We electrified it. We turned it from harmless seasoning into industrial liquid fire. But now we push the experiment further than any furnace on Earth. What happens if you cast salt like metal, in space? To answer that, we need to understand something fundamental. Gravity shapes casting. On Earth, when molten material is poured into a mold, gravity pulls it downward. Density differences create convection currents. Bubbles rise. Impurities sink. Cooling patterns follow predictable vertical gradients. But in microgravity, like aboard the International Space Station, those rules change completely. In zero gravity, molten salt wouldn't pour the way you expect. It wouldn't flow downward into a mold. Instead, surface tension would dominate. The liquid would naturally pull itself into a floating sphere. Without gravity flattening or directing it, molten sodium chloride would behave more like a hovering droplet than a flowing stream. Imagine heating salt past 801 degrees Celsius in microgravity. The moment it melts, instead of cooling at the bottom of a crucible, it would bead up, suspended, shimmering, nearly perfectly spherical. Its ionic particles moving freely, its surface tension holding it together like a tiny artificial star. If you attempted to cast it into a mold, you would need mechanical pressure or centrifugal force to push it into shape. Otherwise, it would resist confinement. And cooling would be different too. On Earth, convection in surrounding air helps remove heat. In space, without atmosphere, cooling happens primarily through radiation. That means the molten salt sphere would lose heat more slowly and more evenly, potentially forming a more uniform crystal lattice as it solidifies. Could that make it stronger? Marginally, perhaps in terms of structural uniformity, but not in terms of fundamental brittleness. Ionic solids still fracture under shear stress, whether formed on Earth or orbit. Now imagine taking this experiment further, onto the Moon. The NASA and other space agencies are actively researching in situ resource utilization, using local materials to build structures instead of launching everything from Earth. Lunar regolith contains various salts and ionic compounds. If refined and melted, could salt-based materials be cast into construction components? Here's where things get interesting. The Moon has 1/6 Earth's gravity. That reduced gravity would change molten flow dynamics, but not eliminate them. Casting would still be possible. Cooling would be different due to the lack of atmosphere. And, crucially, there is almost no humidity. Remember salt's greatest enemy, moisture. On the Moon, there's no humid air to slowly dissolve cast salt structures. A salt object could theoretically last far longer there than on Earth, assuming it isn't mechanically stressed. But there's a catch. Temperature swings on the Moon are extreme, from about plus 127 degrees Celsius in sunlight to minus 173 degrees Celsius in darkness. These drastic fluctuations would cause expansion and contraction cycles. And brittle materials hate thermal stress. Microfractures would form. Over time, even without water, the structure could degrade. Now let's go even further. What if we cast not sodium chloride, but reactive salts. Consider lithium salts. Lithium compounds melt at lower temperatures and have unique electrochemical properties. Or magnesium chloride, widely used in industrial molten salt systems. Each salt has its own melting point, viscosity, conductivity, and reactivity profile. Some molten salts are so chemically aggressive they corrode steel containers. Engineers designing molten salt reactors must use special nickel-based alloys to resist degradation. In advanced reactor concepts like those once tested at Oak Ridge National Laboratory in the 1960s, molten fluoride salts carried nuclear fuel. These weren't just passive liquids, they were active participants in fission reactions. So if you're casting salt like metal in these scenarios, you're not making sculptures. You're handling high-energy, chemically intense fluids capable of reshaping the future of power generation. Now imagine combining casting and additive manufacturing. Could molten salt be 3D printed? In theory, yes. If controlled jets of molten salt were extruded layer by layer into a super dry environment, you could build crystalline structures from the ground up. The rapid solidification might create intricate lattice forms, transparent, geometric, almost alien in appearance. But structurally, still fragile, which brings us to a philosophical twist in this experiment. Metals are valued for strength, resilience, permanence. Salt is the opposite. It is temporary, soluble, vulnerable. Casting salt like metal challenges our definition of what building means. Are we creating something meant to endure centuries? Or something designed to exist briefly, beautifully, and then disappear? Drop a cast salt cube into the ocean, and it dissolves into ions indistinguishable from the sea itself. There is no waste, no rust, no debris, just reintegration. In a world increasingly concerned with sustainability, that impermanence becomes powerful. Imagine temporary architectural structures cast from salt in arid climates. After serving their purpose, they are dissolved and reclaimed. No demolition waste, no landfill. Extreme, yes. Impossible, not entirely. Now let's return to Earth for the final test. You cast a perfect salt blade in a humidity-controlled chamber. It is crystal clear, sharp-edged, geometrically flawless. You swing it through the air. It whistles faintly. It feels solid. Then you strike a steel plate. The result is instantaneous. Not bending, not denting. A shockwave travels through the ionic lattice. Repulsive forces align. Microfractures cascade. The blade explodes into crystalline shards. Because salt was never meant to flex. And that is the ultimate answer to our experiment. What happens when you cast salt like metal? It melts into a clear, electrically conductive ionic liquid at extreme heat. It can be poured and shaped under controlled conditions. It solidifies into a brittle crystalline structure. It shatters under mechanical stress. It dissolves in moisture. It stores enormous thermal energy when molten. It may help power the future of solar and nuclear energy. It behaves completely differently in space. Salt refuses to become metal. And yet, in its molten state, it rivals metal in industrial importance. That contrast is what makes this experiment so powerful. Because sometimes the most ordinary materials, those we overlook daily, contain extraordinary behavior under the right conditions. Salt is not weak. It is simply honest about what it is. Solid, fragile, liquid, powerful, dissolved, invisible. And in understanding that transformation, we don't just learn about casting. We learn about matter itself.